In the last part of the lecture, we'll look at the Cmrr for a source coupled pair with an active load. So let's draw our source coupled pair with an active load. I'm going to diode connect one of the PMOSs. So we have a PMOS current source effectively. We'll draw our NMOS source coupled pair. This is our differential input. We have a tail current source that's connected to a DC bias. Now we already know what the differential voltage gain is for this amplifier. We know ADM is equal to GM times RO2 in parallel with RO4 when our transistors are labeled as follows: M1, M2, M3, and M4. And we remember that M1 is equal to M2 and M3 is equal to M4. Now to find the common mode gain, we're going to tie both the inputs of gate M1 and gate M2 together. And we're going to label a node A here, and we already have our output node here. Now what we know is that we're going to connect this circuit in negative feedback in most instances, and when the circuit is in negative feedback, the voltages in the symmetric terminals should follow one another. In other words, the voltage at node A should be approximately equal to the node voltage at the output. So we can say that VO is approximately equal to VA. They track each other due to symmetry. And if this is the case, then effectively we could draw a short circuit between node A and the output node. Now this short circuit doesn't physically exist, but practically it exists. And if that's the case, then we can draw an equivalent half circuit. And our equivalent half circuit looks as follows. Looking up into the diode connection, both M3 and M4 are diode connected, and they would be in parallel. So we could say that looking up, we'd see 1 over 2 times GM3, 4, in parallel with the output resistance of 3 and 4. Now, of course, 1 over GM is going to be much smaller than our output, so we can typically neglect that output resistance. This is connected to a transistor. M1 is effectively in parallel with M2, which doubles its size. And this means that this transistor has a GM that is 2 times GM1, the GM of either the individual transistors M1 or M2. The output resistance of M1 and M2 are effectively in parallel, so we can say that the output resistance of 1 and 2 are divided by 2. And finally, we look down towards the tail current source, and we see that tail current source RO5. So our input is here, VI. Our output is in the same position that it was before, VO. And if we write the voltage gain for this circuit, we'd have to find the big GM and the R total at the output. Big GM, we know, is equal to 2 GM1, 2 over 1 plus 2 GM1, 2 times RO5. Our R total is equal to RO1, 2 over 2 times 1 plus twice GM1, 2 times RO5 in parallel with 1 over 2 times GM3, 4. So we can say that this whole thing is approximately equal to 1 over 2 times GM3, 4, because 1 over 2GM is going to be much smaller than RO times 1 plus 2GM times RO. Alright, so solving all of this, we can say that our common mode gain, ACM, is equal to approximately GM1, 2 over GM3, 4 divided by 1 plus 2 times GM1, 2 over RO, 5. Now this should be quite a small common mode gain. We can assume that the GMs 1 and 2 are probably approximately equal to the GMs of 3 and 4. So this numerator is approximately unity, and the denominator is a very big number. It's the GM1, 2 times the resistance, effectively. So, to find our common mode rejection ratio, we have ADM divided by ACM, and we can write that it's equal to GM1, 2 times RO2 in parallel with RO4 divided by GM1, 2 divided by GM3, 4 over 1 plus 2 GM1, 2 times RO5. Or, simplifying this expression, we see that it's RO2 in parallel with RO4 times 1 plus 2 GM1, 2 times RO5 divided by that'd be times GM3, 4. Alright, so we expect this to be quite a large number, the common mode rejection ratio for this particular amplifier. Now, one last thing to show you is how do we determine what we know that in an operational amplifier we have a non-inverting terminal, inverting terminal, and our output terminal. How do we determine on this particular amplifier what is the non-inverting terminal and what is the inverting terminal? And to do this, we're going to use our perturbation analysis technique. We're going to perturb one of the inputs and see what happens to the output. In other words, we're going to put a positive voltage on this terminal. So we're going to put a plus delta V on this terminal and see what happens at the output. Okay, so if we put a plus delta V on the terminal that we're looking at right here, VI1, we'll label this VI2. We put a plus delta V on terminal VI1, we'd see that more current would flow through this branch. So we'd have an increase in current in this branch. Now that increase in current in this branch flows into M3 here and is mirrored over through M4 to the output. So we'd see more current flowing through M4 coming from the positive supply. So we have a higher current coming from the positive supply going towards the output node. So we should see the output node raise in voltage. And so we can say that this terminal is our non-inverting terminal because an increase in voltage at this terminal causes an increase in voltage at the output terminal. Now to double check, we would think that that would mean that VI2 here would be the inverting terminal, and let's just check that assumption. Alright, so if we increase the voltage at this node, we see that more current will flow through transistor M2 towards ground. In other words, we'd be lowering the output node voltage. So we increase the output voltage and we'd see a decrease in the output voltage. And so that is the case. So VI1 is our non-inverting terminal, and VI2 is our inverting terminal for this particular amplifier. So that will end our first lesson in making an op-amp. We have our source coupled pair with an active load. and we will start investigating more operational amplifier topologies as we go along.